What up, my students? Today's section is 5.2. That's right, we're going back to 5.2. It's polynomial terminology. For all of you who didn't know what polynomials were, I'm finally going to define this for you. For all of you that didn't know or didn't care, whatever, like here it comes. The essential question, what is a polynomial? What do they look like? Probably I should have put an Oxford comma here. And how can I describe them? One of my few consolations left in life is looking up math memes. Just take a look at this math meme. It does not relate to what we talked about today, but it relates to something we talked about in last night's video. If you can't figure out why this is funny, then maybe you just don't know math good enough. Anyway, here's a polynomial in standard form. So, first of all, what is a polynomial? The defining characteristic of a polynomial is this. Let's look at the exponents. 4, 2. Since I don't see an exponent here, I could write 1. And over here, I have a term without a variable and an exponent. But couldn't I write x to the 0? Because, technically, x to the 0 is just 1. So writing that there is just the same as writing 3 times 1, which is still just 3. So I'll write it there just so that we can see that there is a pattern here. What do we notice about all of these exponents? Well, they are whole numbers. So that's the chief feature of a polynomial. All of the exponents are whole numbers. And in front of the base, which is a variable, you can have any kind of coefficient you want. We'll talk about some non-examples later on, but just know for now, polynomials have whole number exponents. There are a couple of parts I need to define in this polynomial. First of all, this is in standard form, meaning it is in order from highest exponent to lowest exponent. So 4, 2, 1, 0, order from highest to lowest. So it's in standard form. Next, we need to define the degree. The degree of a polynomial is the highest exponent. In this case, it is 4. So the degree of the polynomial is 4. Next, let's talk about the lead coefficient. Remember, the coefficient is a number that's multiplying a variable. So the lead coefficient is the first one of those. In other words, 3. 3 is the first number that's multiplying the highest powered variable. So lead coefficient. Finally, some polynomials, but not all of them, have a constant term. The constant term is the lonely guy at the end who has no variable attached to him. In this case, the constant term is -3. So let's put these definitions to the test in the next slide. We're going to identify some stuff. First of all, let's look for the lead coefficient, the degree. They kind of go together, right? Look at this polynomial here. I have 3x to the third minus 2x to the 7 plus 4x minus 8. Is it in standard form? Actually, it's not in standard form. And the reason why is because, look, the 7, the exponent 7 is behind the exponent 3. So let's put it in standard form quickly by simply rearranging those first two terms. So -2x to the 7 plus 3x to the 3 plus 4x minus 8. Now I have standard form, and so it's easy to identify the lead coefficient. That would be -2. It's also easy to identify the degree, which remember is the highest exponent. That is 7. Constant term is the one without a variable. That is -8. It's easy. Here are some examples and non-examples. Remember, a polynomial has only whole number exponents. So we need to check each one of these to see if they have whole number exponents. And remember, the coefficients can be anything as long as there are whole number exponents. So let's look at this first polynomial. Whole number, and this would be like x to the 0, also a whole number. So this is an example of a polynomial. Yes, check. This is a polynomial. Now let's look at this next one. I have some weird things in there. The square root of 3. Whoa. Pi. Whoa. But remember, I'm only looking to see if there are whole number exponents. In this case, x to the 1. Yeah, that's a whole number. This square root of 3, as weird as it is, isn't this the constant term? So this is the term that would have like an x to the 0. So also a whole number exponent. And as weird as this pi is, the variable it is attached to has a whole number exponent. So this is an example, and that's happy because I can make another check mark and they look good. This next one, 2, it's a whole number. -1, ooh, -1 is not a whole number. So remember, whole numbers are only positives and 0. Also remember, we hate seeing negative exponents. It's weird, we don't know how to deal with them. So because of that negative exponent, this is a non-example. -1 is not a whole number exponent. Finally, x to the 1, good. Whoa, 2 to the x. That's really weird. That's not, x could not be a whole number. Like, it's weird to see x in the exponent. X could not be a whole number. So this is a non-example. Oh, why did I make a check mark there? I guess I was really happy with my check marks, but non-examples deserve x's. So remember, whole number exponents, that means it's a polynomial. Sorry, this is a bit of an info dump. We'll keep moving on. Just be glad I'm not doing this in class A. There are some special types of polynomials we have already dealt with. Take a look at this. It is a constant polynomial. F of x equals 3. If you remember, that is just a straight horizontal line. And even though it's a line, technically it does count as a polynomial because look, this is just the constant term. It has that x to the 0 I keep mentioning, which is a whole number exponent, so it's a polynomial. Next, we have a linear polynomial. Is this a polynomial? Yes, because it has all whole numbers. Even though it's just a lowly line, this still counts as a polynomial. Also, the most complicated polynomials we've dealt with are quadratic polynomials. Yes, these are also polynomials. They have all whole number exponents. And this would be doing something like this. That technically also counts as a polynomial. So what's new this chapter, you say? Well, look at this. Whoa! Exponents, craziness. This is called a cubic polynomial. The reason it's called a cubic polynomial, cubic denotes 3, and the degree of this polynomial is 3. Remember, degree is the highest power. So this does crazy things, and polynomials can start doing crazy things. Here's the graph of this, and I think this is a very interesting graph, maybe the most interesting graph you've ever seen in your life. Let's take a look at a few features of this graph that are not necessarily new, but that we just need to apply to polynomials. First of all, remember the term 0. 0 was everywhere the graph crosses the x-axis, or in other words, x-intercepts. So I marked the zeros with a dot, and remember 0 is a synonym for x-intercept. We could also label some other things like the y-intercept. Here's the y-intercept. And interestingly enough, remember how back in quadratics we cared about the maximum and minimum? Oftentimes with polynomials, we will have what are called relative maximums and relative minimums. So let me label those in green, and I think you'll see what I mean by a relative maximum. See what the graph is doing? It kind of comes up and then it goes back down. Over here, ultimately the graph is higher than over here. But if I'm just looking at this section of the graph, wouldn't we agree that this is a maximum of just this section of the graph? So we call this point a relative maximum. Because even though the function's going to get higher later on, right here it is a maximum. Similarly, even though the graph gets really low over here, if we look at just this part of the graph, we see that there is a relative minimum there. Pretty interesting. So this is a relative minimum, or a rel min if you're abbreviating. So relative minimum, awesome. So those are some things you probably already know how to do in your calculator. But I need to talk to you about one more thing. Actually, just kidding. This video is getting long. Let's do that one more thing in class because I want to show you an even crazier polynomial, and that polynomial is a quartic polynomial. Quartic denoting 4. This has a degree of 4. So first of all, let's label some things. First of all, let's label the relative extrema. When I say relative extrema, what I mean is it's either a relative max or it's a relative min. So relative extrema just refer to, hey, I'm hitting an extreme value. It's either a max or a min if we're looking at that small little section. Here is a relative max, so it counts as a relative extrema. Here is a relative min, so it counts as a relative extrema. And here's another relative max. That's pretty crazy. There are 3 relative extrema in this quartic function. I can also label the y-intercept. So let's do that in blue, just like on the last slide. Y-intercept is right here. Y-intercept. And finally, we can label the zeros. Remember, the zeros are the x-intercepts. So it looks like it crosses here, 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 and here. Here's a pattern I want you to notice. How many zeros does this function have? Looks like it has 4. What's the degree? This last one, how many zeros does it have? What's the degree? So that's not always the case, but as it turns out, the maximum number of zeros a polynomial can have is the degree. And if you remember, a quadratic, which had a degree of 2, had at maximum 2 zeros. All right, that was a bit of an info dump, but thank you for watching. To summarize for you, a polynomial must have whole number exponents. And forget about this other one. We are going to talk about end behavior in class, so don't look at it for here. Maybe if you're lucky, I'll make another mini video about end behavior as it is a bit complicated, but we will talk about it in class. Thank you for watching as always, guys, and if you weren't listening to the sound of my voice, you really missed out. Start the trend of listening to these videos with volume, otherwise you are doing your education a disservice. Cheers.